At the end of the previous video, we proved that the Schwarzschild singularity, which lies at the Schwarzschild radius, is not really a singularity, a physical singularity. It is just the consequence of a path choice of coordinates. And we proved that by writing the Schwarzschild metric in better coordinates, the Eddington-Finkelstein coordinates. In those coordinates, the metric is regular at r equal rs, the Schwarzschild radius. Let me draw it like this. Okay. R equal to rs. So these two coordinate systems, the standard Schwarzschild coordinates and the Eddington-Finkelstein coordinates, are related by a standard invertible change of coordinates in the exterior. Of course, over this surface r equal to rs, the change is not invertible anymore, and this is why the Eddington-Finkelstein coordinates are regular there, while the other set of coordinates are bad. And it's in the interior they are not related at all in principle, okay, because in the standard coordinates we can only trust the exterior of this region r equal to rs. However, we showed that the Eddington-Finkelstein coordinates also reach the interior. They are regular outside, but they are also regular in the interior of this r equal rs region. Then what we achieved, apart from proving the regularity of this so-called Schwarzschild singularity, we proved that there is another region in the space-time apart from the exterior. Okay, this interior of, let's use the standard name. This is the horizon. This will be the horizon of the black hole. So the interior also belongs to our space-time. And this is what we have done is an analytical extension of the Schwarzschild metric from the exterior that was described by the standard coordinates to the interior. This is, however, not the maximal analytical extension that one can perform, and this complete space-time is much larger than this. This was realized by Sinch and other researchers, and the easiest way to describe or to find this maximal analytical extension is by using the so-called Kruskal-Szekeres coordinates. Okay, they were discovered independently by these two people. And this is what we are going to do in this video. We are going to perform the change of coordinates and rewrite the Schwarzschild metric in such a way that it will be regular not only in the exterior and the interior, but also on another two regions which are not covered by the Eddington-Finkelstein coordinates. The starting point of this change of coordinates are the Eddington-Finkelstein coordinates. However, we are going to use not the set u r theta phi or v r theta phi. We are going to use, instead of r, the other Eddington-Finkelstein coordinate, the other null coordinate. So we start with this metric that in fact we wrote at some point, which depends on the coordinates u, v, theta, and phi. Remember that using this tortoise coordinate r star, we manage to write the metric in this way. Okay, where now r is to be considered a function of r star, which is the tortoise coordinate. The main property of the tortoise coordinate was that dr divided by lambda was dr star, and this is what allows us to take this lambda as a common factor here. Then we remember what was the definition of u and v. Okay, v was defined as t plus r star, and u was defined as t minus r star. So the differentials are as you expect, and this automatically is du times dv. So we are now working in u v coordinates, and the metric has this form. Okay, sometimes I write this 2 here, and that's because in higher dimensions naturally you get the metric of unit 3 spheres, 4 spheres, and so on. Okay, here we are always working in 4 dimensions in this course, so there is no need to write this 2, but you know, I have this habit of writing the 2. Okay, here in this expression r, okay, remember that r was a function of r star, and r star is a half of v minus u. Okay, so in the end, r is a function of u and v. Okay, and so the whole metric is a function of u, v, and theta and phi. Okay, so the next step will be to change from these coordinates small u and small v to some other coordinates, which are the Kruskal coordinates, which are capital U and capital V. Why do we need to do this? Observe that even though in these coordinates t and v, if we are working in Eynton-Finkelstein coordinates, we choose r and v or r and u, and in those coordinates the metric was regular at r equal to rs. However, in these coordinates u and v, the metric is not regular at rs, because at rs this vanishes, and the metric, which we can write as, as a matrix form in this way, and here this is the angular part, which doesn't matter very much. The determinant is proportional to lambda squared, and if lambda vanishes, then the determinant vanishes, so the metric is still singular there. This is why, although we introduced u and v, we never use them together in order to construct a metric regular at the horizon. Still, using these 2 coordinates is useful to arrive to the Kruskal coordinates. Okay, so let me go back and eliminate this. Now the definition of these coordinates capital U and capital V is as follows. So u is defined as minus the exponential of minus u divided by 2rs. Okay, and uv is the exponential of v divided by 2rs. And observe that according to this change of coordinates, u should only take negative values, and v can only take positive values. However, if in the final metric that we find there may be no restrictions for the value of u, it may happen that the metric that we obtain is valid for all values of u, positive or negative, and the same for v. In that case, if that's the case, then we will have extended the original metric to a region that was not covered by small u or small v, because the regions covered by small u and small v were the regions in which u is negative and v is positive. Okay, so everything is almost ready to find this analytical extension. The only thing that has to happen is that in the end the metric is well defined for all values of u and all values of v. So in order to change coordinates, we just differentiate these definitions, and we get that the differential of u, you take the derivative of this, you get a factor of 1 over 2 rs, and then you again get the exponential and the u, but the exponential is minus u, so you can write this. Okay, and then it will be easier to replace the u as a function of capital U. And you do the same with v, so you get 1 over 2 rs v dv. du dv, capital U and capital V, then is nothing but minus 1 over 4 rs squared u v du dv. Okay, and you may, if you want now, this is how it is often done. You may use these definitions because the product of u and v is plus e to the v minus u divided by 2rs du dv, and v minus u, we just so that it is r star, so this is 1 over 4rs squared, e r star divided by rs du dv. And then if we remember the expression for r star, remember that r star was r plus rs and then the log of the absolute value of r divided by rs minus 1. Okay, if we use this here, we write 1 over 4 rs squared r divided by rs, and then the exponential of the log of r minus rs. So this is r divided by rs minus 1. Okay, du dv, and okay, this is nothing but r times rs, r divided by rs times lambda. Okay, so we take this outside, and this is 1 over 4 rs squared, and the absolute value of r divided by rs lambda, the exponential of r divided by rs du dv. And now we go with this to this expression where there is a lambda, and okay, we express first this du dv small with respect inverting this function, and we get ds squared. We have a lambda originally, we have now 4s squared, and we divide this by r divided by rs, lambda absolute value e to the minus r divided by rs du dv minus r squared d omega squared. The purpose of we could have lived with this u and v there, but it is better to go back to this r, because then we will show explicitly that this metric is regular at r equal rs. In fact, you see already that this lambda and this lambda will cancel, they only give you a sign. So we keep calculating. Okay, and we get 4rs cubed. This will be divided by r, r is always positive, and then we have lambda, well, e to the minus r divided by rs, and then here we have the sign of lambda, which is also the sign of r minus rs. So when r is larger than rs and we are in the exterior, we know that lambda is positive, okay, and also r minus rs is positive, and vice versa. And we have this times the u dv minus r squared the omega squared. Okay, the final word is not in terms of this u and v. You already see that this metric has an expression which is regular, absolutely regular at r equal rs. So, well, we have eliminated this lambda that was the origin of the problem of this metric. The metric is now regular there, and often this metric is left as it is, but a final step that one can do is the following. We define some new coordinates, capital T and capital X, and we define them in this way. So we find sine r minus rs times u. This is t minus x, and v is t plus x. Okay, if these are null coordinates, these are t is time-like coordinate and x is a space-like coordinate. Okay, and this means that this part here is just dt squared minus the x squared. So finally, in these coordinates, the metric takes this form, and dt squared minus the x squared minus r squared the omega squared. And this is the Schwarzschild metric in Kruskal coordinates or Kruskal-Szekeres coordinates, where r is supposed to be now a function of this capital T and x. Now, if this metric is regular for all values of t and x, which means all values and all signs of u and v, we probably have extended the Schwarzschild metric to other regions. And this is, in order to see this, we have to study this metric. Okay. So, in order to see exactly how this comes about, we want to relate these new coordinates, capital T and capital X, to the old coordinates T and R. Okay, this is implicit here, but we want to find this explicit change. And there are certain combinations which are easier to deal with. So t, for instance, t squared minus x squared, this is equal to, by definition, of sine r minus rs times u and v. And if we remember the definition, this is minus the sine of r minus rs and the exponential minus u to rs and e exponential of v divided by 2 rs. Now remember that we have here v minus u, this was r star divided by rs. Okay, the factor of 2 is in the given. Okay, this is minus the sine of r minus rs, and r star is just r, so this is r divided by rs, and this was sorry, now we have the exponential of the log of the absolute value of r divided by rs, or, well, I think we can express it in this way. But now, okay, before we finish, see that when r is larger than rs, this is positive, and you have this plus sign, and vice versa. So you can remove this sign here, this whole thing here, and the absolute values. And now you take the minus sign to invert this relation. You have 1 minus r divided by rs, and the exponential of r divided by rs. So this gives you this combination, t squared minus x squared. And now you consider the quotient t divided by x. And okay, let's do it first for r larger than rs. So t divided by x is just v plus u, and x is v minus u. Both of them have a factor of 1/2, but they cancel. And now v plus u, okay, these are exponentials, so let me write everything explicitly. This is v divided by 2rs minus e to the minus u divided by 2rs, and here you get the sum plus e minus u divided by 2rs. Now you can multiply numerator and denominator by by the exponential of u divided by 2rs, and then you get here u plus v divided by 2rs minus 1, and here u plus v divided by 2rs plus 1. And okay, now you could now multiply both sides if you wanted by e to the minus u plus v divided by 4rs, and then you would see, okay, and here the same, divided by 4rs, and then you would get the hyperbolic sign of u plus v divided by 4rs divided by the hyperbolic cosine up to a factor of 2. So you would have to divide this by 2. Again, it doesn't really matter much. So cos u plus v divided by 4rs, which is the hyperbolic tangent of u plus v divided by 4rs. Now u plus v, small u plus v, is 2 times t. So this expression is the hyperbolic tangent of t. So u plus v is 2 times t, so that you get t divided by 2rs. And if r is smaller than rs, when you take this quotient, the main difference is in these signs, because of this sign here. Okay, now u comes always multiplied by a minus sign, so now you get v minus u divided by v plus u, which is the inverse of this, which is the cotangent, the hyperbolic cotangent of t divided by 2rs. Okay, these are the main two relations, and now you can combine this and this in order to have separate expressions for capital T and capital X in terms of r and small t. So let me do it quickly. If t squared minus x squared is some expression that I call a, and t divided by x is some other expression that I call b, so t is equal to bx, then replacing t by bx here, you get x squared, b squared minus 1 equal to a, and x is equal to the square root of a divided by b squared minus 1. This will be 1, and then from here you get that t is equal to b times the square root of a divided by b squared minus 1. Now A here is this expression. Okay, and of course I have to distinguish between these two cases. So first I have to consider R larger than Rs. Okay, and here X will be the square root of A, which is 1 minus Rs, R divided by Rs, sorry, and the exponential of R divided by Rs, and B squared, here B squared for R larger than Rs is the hyperbolic tangent of T divided by 2Rs squared minus 1. This gives you, okay, if R is larger than Rs, you have to take into account that this expression is negative. Okay. So you probably want to write minus R divided by Rs minus 1 E R divided by Rs. And here you have a hyperbolic sign. Well, there is a hyperbolic cosine that appears here, squared, and this should be divided by by minus 1. Okay, because you have sine, hyperbolic sine squared minus hyperbolic cosine squared. This gives you minus 1. These two signs cancel, and this expression is just a square root of R divided by Rs minus 1 e to the R divided by 2Rs and the hyperbolic cosine of 2Rs. Okay, this is X in this case, and T I just multiply by the hyperbolic tangent, so well, is the same, R divided by Rs minus 1 E R divided by 2 Rs and a hyperbolic sign. Now, if you do the same for R smaller than Rs, you get similar expressions, but with hyperbolic signs and cosines interchanged, and these expressions reversed. So you have a square root of 1 minus R divided by Rs e to the R divided by 2Rs, a hyperbolic cosine T divided by 2Rs, and for T you have the square root of 1 minus R divided by Rs e to the R to Rs and hyperbolic sign. Okay, so these are the relations. You see that there are, first of all, we have achieved analytical extension to the region R smaller than Rs. Okay, here there is a relation between this X and T to the old coordinates that we were not so sure if they were valid inside, but clearly this X and T for these values cover the interior. But then there is also another thing, which is that these square roots have two different roots, positive and negative. Okay, you have to take the same in both places. So you have plus and minus, and plus and minus. Okay, this sign are the same as this, but they are unrelated in principle to these ones. And this means that we have two R larger than Rs regions, okay, which are covered for positive and negative values of X and T, and two R smaller than Rs regions, which are covered for these two possible roots, positive and negative values of x and t, which are related to the positive and negative values of u. This is what I warned you at the beginning, that when you start with u, small u and v, you exponentiate, it looks like this capital U principle can only take a certain number of values, but you see now explicitly in this metric that the metric is regular for all values of x and t. Now the thing that you have to prove is that this factor you have here that depends on the small r, where r is a function of capital T and x, is a regular function of t and x everywhere except maybe at the points where r is 0. Okay, you know that this is going to happen because r is dividing. Okay. But the only place you should worry about in principle is r equal to rs. These functions are regular there, but it might happen that, I don't know, I think that this function r as a function of t and x has a problem. It shouldn't, but okay, you can check that there isn't. The consequence is that we started with one region, okay, the exterior of let's call it black hole already, okay, and a single exterior. We have extended the metric now in 4 different ways. It looks like we have 2 exteriors and 2 interiors, and we have to now to draw some kind of diagram in order to see this with our own eyes, to see what it means. So it's going to be a diagram in terms of the Kruskal coordinates capital T and capital X. So this is capital T and capital X, and this is a diagram in which we represent a 4-dimensional metric. It's a 4-dimensional space-time, so you have to imagine that well, at each point in this Tx diagram there is a true sphere whose radius is given by this function of t and x. Okay, and this gives you the full space-time. This is enough to study this radially directed geodesics and so on. Okay, so now we know that there is a singularity at r equals 0, a physical singularity. This is something that we proved. Okay, now if we look into these expressions, okay, r equals 0 means t squared minus x squared equal to 1. Okay? The exponential is 0, so it's this, and this is a hyperbola, but the hyperbola that has 2 branches. So this corresponds to r equals 0, and this also corresponds to r equals 0. So this is t squared minus x squared equal to 1. Equal to 1. Okay, another thing that we can draw is this surface r equal to rs. And now, if r is equal to rs, we come here, is equal to rs, t squared minus x squared is equal to 0. But the solutions to the equation t squared minus x squared equal to 0 are 2. Okay, t squared minus x is equal to x squared. This means that t is equal to plus or minus x. Okay, and these are these 2 lines at 45 degrees. So this is r equal to rs, but this is also r equal to rs. Okay, the lines of constant r but r larger than rs are this kind of hyperbolas. They are always doubled, okay? You have two branches. Okay, they are like this, and they are more and more open when r goes to infinity. So r is growing here, okay? And it is decreasing until r is equal to rs. And when r is smaller than rs, but different from 0, you get this kind of hyperbolas, and the same here. How about the time coordinate? Well, the time coordinate, if you want to look at it from here, the best way to do it is to look at this expression, okay, where you get the constant, the quotient t of t and x, and for constant values of t. And you see that for each constant value of t, this hyperbolic cotangent, or the hyperbolic tangent, is some number that gives you the proportionality between t and x. So these are straight lines with a slope that is given either by this tangent or by the cotangent. And you can check that these straight lines, these are straight lines that cross the origin. They move forward in time in this way. So time evolves in this way here. And this I have represented here surfaces of constant r and surfaces of constant time. Okay, another thing is that in the interior, as you know, these surfaces of constant r, with r smaller than rs, are now space-like. Here they are time-like, as they should be, just as the same as the surfaces of constant t are space-like here, but here they are, well, I said space-like, and then they are time-like. The roles of t and r are reversed in the interior, okay? The interesting thing is that in this kind of diagram, you already see that, well, first, notice that the light cones in this diagram have the same shape as in Minkowski spacetime, because this part of the metric is conformally flat. Okay, you get some factor times dt squared minus d squared, which would be the Minkowski metric in one dimension. If you multiply by a number, the angles will not change. So since it is only on the angles that the light cones depend, here in this diagram, light rays will propagate at 45 degrees in one direction or the other direction. Okay? This will be your incoming light rays, and this will be your outgoing light rays. Okay, they go to larger distances, to larger values of x, which will correspond to larger values of r. Okay, this is something that you can check. These curves go asymptotically to this one. Okay. Now you see that already this is difficult to see in this diagram, and this is why there is a better diagram to distinguish certain things like, okay, are these light rays going to reach infinity, so they are going all the time to grow in values of r? This kind of questions can be answered much better by looking at a Penrose diagram, that of which I will tell you in a second. Now, interesting thing is that the outgoing light rays, or what would be outgoing light rays here in this region, okay, remember that this is a hyperbola, so it is also asymptotically reaches this line, which means that any light ray which is directed in this direction could be outgoing it is not really outgoing in the sense that it will go to larger and larger values of r. It really goes to smaller and smaller values of r, and in fact, it always go to r equal to 0 where the singularity is. Furthermore, anything which is inside, not just light rays, as you can imagine, because the light cones are like this, okay, they have to move into this direction, and at most they can reach the speed of light. But if you are inside, you can never reach this line, the line r equal rs, and you can never communicate with the exterior. This gives you the idea that this barrier we talked about, which is the black hole horizon, is something serious that takes place in the whole space-time. Now, the region that we described at the beginning, which is described by the standard Schwarzschild coordinates, is the region r larger than rs, but there are two regions like this. Okay, this is the region 1. The interior that we discovered with the Eddington-Finkelstein coordinates is here. There is another exterior here, and in fact another asymptotic infinity here. Okay, and here there is another singularity, but it's a singularity that you can never reach because you move forward in time, so you can never reach it. But things that come eventually from this singularity, they may reach you. This is the singularity of the black hole. Okay, the horizon is all this. This is a horizon which is called a bifurcate horizon because it has this place where these two branches of the horizon intersect, which is called bifurcation surface or bifurcation sphere, because in this case it is a two-sphere. Remember that each point in this diagram is a two-sphere of a certain radius. And now I'm lost about what I was telling you. I was going to tell you that this is this region is called the white hole. Okay. In a sense, this region is the contrary of this one. Nothing can get out of this region, and everything gets out of this region, always, one way or the other. It may end up in this one or in the regions 1 and 3, but you always get out of region 4. Another thing is that you can never communicate region 1 with region 3. You would have to go faster than the speed of light. You can communicate with people coming from region 3 because they can fall into the black hole through their own branch of the horizon, and you could fall in this direction as well, and then you may meet. But certainly this is not a desirable situation, because then you are always going to end up in the singularity. In the singularity, the curvature blows up, which means that tidal forces blow up and everything is destroyed. But this singularity, it is not really a place. The fact that it is space-like means that it is in your future. It is at a constant. It is not a constant value of time, but it is similar to any other space-like hypersurface, which, for instance, some of them are given by a constant value of time. In this case, there are different values of this time, capital T, but the point is that they lie on your future. So you cannot see it, because any signal coming from it will have to travel backwards in time for you to see it. This is more difficult to see here. It looks like, okay, maybe if I am here, I will be... No. Any signal has to travel faster than light in order to reach you, so you can never see it. You will just end there in your future. Okay, the singularity is not at a place, but at a time. Well, I mentioned that there is a better way to describe these space-times, and in particular what we call the causal structure of the space-time, which is what is the place where light rays which are directed to the future and also outwards end, or where which is the infinite where time-like geodesics end, okay, which are the world lines of massive particles and so on. The way to see this is to bring infinity to a finite distance. And you do this certainly not by a change of coordinates, because a change of coordinates would preserve things like proper distances or proper times, but by a conformal transformation. This is the idea of the Penrose diagrams. You perform a change of coordinates and you perform a conformal transformation, and you find a conformally equivalent metric, which is such that it is described in coordinates such that you reach infinite for finite values of your coordinates. So let me explain this very briefly, because this is not supposed to be in the program. Okay, for Minkowski spacetime, you can do this, or for any other spacetime. And if you do this for Minkowski spacetime in spherical coordinates, you could take the whole spacetime, okay, which you can imagine as this would be r equals 0, okay, and so there is the r coordinate and the time coordinate, and if you use this radial coordinate, there is no left hand side of this diagram, but it could be this infinite region. Now you can perform this conformal transformation, and to bring the infinity to this to a finite distance, as a matter of fact. Okay. This the whole Minkowski spacetime is reduced to this triangle. Again, there are two spheres at each point, and the properties of this triangle are that all light rays which are outward directed to infinity, they end up here, okay, and this is called the future null infinity of this region. Okay, in fact, in the Kruskal diagram, there must be something like this, because all these light rays end up somewhere, but this somewhere is really at infinity. You don't see it. When you perform this conformal transformation, you bring it to a finite distance, and this is now your script plus script I. Okay, there is past null infinity, which is where all light rays which are incoming, okay, come from. There is space-like infinity, which is I0, and this is where all space-like geodesics end. Okay, and it doesn't matter where they come from; they always end there. Also, all time-like geodesics start at this place, which is the past infinity, and they end up here, which is the future infinity. Okay, the future time-like infinity. Sorry, and this is the past time-like infinity. Okay, in fact, any time-like world line will start here and will end here. It looks like a bit surprising that all of them come from the same place. Okay, this is a two-sphere, but this is an effect of the Penrose diagram. Now, in Minkowski, maybe it's not that interesting, this Penrose diagram. If you do the same, and I'm talking about this very schematically, for the Schwarzschild spacetime, what you find is something like this. This is the Penrose diagram for the Schwarzschild spacetime. Okay, I don't want I want this to be a curved line down. Okay, something like this. And okay, just recognize these 4 regions. The 2 singularities are equal 0. Here is where all outgoing light rays go to. This is scribe plus, the future null infinity. This is where all ingoing light rays come from. This is scribe minus. This is space like infinity. This is the time like future time like infinity and past time like infinity. And you see that there is no future null infinity here or anything like that, because light rays that could be outgoing, because we have considered that these directions are generically outgoing, they are not really outgoing. They don't go all the way to infinity, they go to the singularity. Okay, so this is why scribe plus is only here. Only light rays outgoing, light rays which are in the exterior of the Schwarzschild metric can reach infinity. And basically this tells you what the definition of a black hole can be, because you can characterize the black hole as the region from which nothing can reach this infinity. So nothing which is inside of the black hole can ever be seen, even if you wait a lot of time. Okay, you are looking here in some place very far away, and you will never get any signal from the interior of the black hole. Another important thing is that you only call this a horizon after you see this Penrose diagram and you have found what is the complete structure of the space-time. Okay, the horizon, this is something that we will discuss in the next lecture, is a global notion. It's not a local notion. This implies that we need to know the whole history of the space-time. You cannot just, it's not enough to have knowledge about what happens at a certain time. Okay, this would be a section of our space-time for a constant time, and then we may know the metric here. This is what happens actually, because we know how the universe is and how things are at a given time, but that's not enough. Unless we know the whole history, we cannot say where the horizon is. And this is a bit in contrast with the way we want to observe black holes in astrophysics. We accept that there is a horizon there and blah blah blah, but truly the concept of horizon is a global concept, and we are using approximations when we are talking about the horizon of an astrophysical black hole. People have tried to find local notions of horizon, local in the sense that you don't need to know the whole history, that you just need to know local properties of the gravitational field in the neighborhood of your putative black hole, for instance. But none of those definitions satisfy the very nice properties that the standard notion of horizon satisfies. And this is why they have not been adopted. There are other notions which are interesting, like that of trapped surface or trapped region, and so on. And there are quasi-local definitions and so on, but the only ones that really do the job are this global definition of horizon. So this is an appetizer for the next lecture, in which I will try to discuss, to tell you about more general kinds of black holes. We will see more metrics describing black holes, and we will try to find what are the common points shared by all those metrics. Okay, the existence of this horizon and how to characterize this horizon and what the properties are.